Hi everybody, so we're going to talk about the central limit theorem today. This is going to be the last section for chapter 6, which is related to normal distribution. We'll be using some of the knowledge we've learned before for normal distribution to solve the problems in this section here. So for central limit theorem, it's related to the sample mean x bar. Okay. So I'd like to remind you guys for x bar, it is for sample mean. So when you see the symbol here, x bar, you remember that's for sample mean, right? So sample mean comes from a particular sample. And we know sample changes, therefore sample mean x bar is a random variable. Okay. So here we are interested in x bar. So x bar is a random variable. And if it's a random variable, then it will have a distribution, right? Distribution. And this is called sampling distribution of x bar. As for distribution, we would be interested in the central tendency, which is the mean, and the spread of the data, which is called the standard deviation, as we mentioned before. So the central limit theorem that is simply covered in this section basically just talks about the distribution, mean, and the standard deviation of the sample mean x bar. Okay, because as we have mentioned, x bar here is a random variable. So let's look at the central limit theorem. So central limit theorem says, okay, if we take a sample of size n from a distribution with mean, mu, and a standard deviation, the sample mean x bar may take on a whole range of values, some more likely others, and the mean of the distribution x bar is simply denoted as mu of x bar, okay, mu's of sub x bar. So means of the sample means, because over here x bar is our random variable. Again, let's refer here, x bar is our random variable. Okay, so it's the mu, it's the mean of this random variable. Now, the standard deviation of this sample mean, standard deviation of sample mean is also denoted by sigma of x bar. Again, x bar here refers to the random variable we are interested in, and sigma is for standard deviation. So basically the notation are pretty similar to what we had before, only the difference is we're adding this the subscript here for the random variable x bar. Alright, so next is our real central limit theorem, what this is about. So central limit theorem talks about the distribution of x bar. Okay, so therefore there are two items that we are interested in. One is the mean of that random variable x bar. The good thing is mean of x bar is the same as the mean of the original population. So the mean of the distribution of sample means is the same as mean of the population being sampled. So same central tendency. Okay. Secondly is about the spread. So sigma of x bar, the standard deviation of sample mean x bar is the population sigma, population standard deviation, and then divide by square root of the n. Here n is the sample size. Okay, I want to mention here this n is the sample size. So which means how widely spread those x bar is somehow depend on how big your sample size is. Okay. It's going to be your population standard deviation, sigma, and then divide by this additional item, square root of n. Okay. So then the central limit theorem kicks in. Okay, so central limit theorem kicks in. It says the distribution of my random variable x bar is approximately normal. So that's a good thing, which means everything we have learned before about normal distribution can be applied to x bar, such as using StatCrunch to compute their probabilities. But there are some conditions we'll have to meet. Okay, so as long as one or both of the following are true. The first condition is the original population is normal. Original population is normally distributed. So which means if the sample comes from a normally distributed population, then the sample mean is also approximately normal. Second, okay, If you can meet this condition, the central limit theorem can be also applied. The second condition says sample size is large enough. And we say large, basically it's talking about the sample size being greater than or equal to 30. So as long as one or both of these followings are true, you can use central limit theorem and conclude the distribution of x bar is approximately normal. Okay. So here's a summary. Okay. Which is regarding to the notations and central limit theorems here. So let's look at some of the notations. Population being sampled has mean mu and standard deviation mean. And the corresponding sample means x bar as a random variable has the same mean, okay, as this mu, but standard deviation is sigma over root of n, as we just mentioned. The original population may or may not follow a normal distribution. It depends on what population you're looking at. And we are taking n items being sampled from the distribution, getting the sample mean. So the last part that we have here is the central limit theorem. Central limit theorem here saying that the x bar sample means they would follow a normal distribution if either sample size is large enough, greater than or equal to 30, and or the original population follows a normal distribution. All right, so that's a quick summary of what the central limit theorem talks about. Okay, so in general, if we know that x bar, which is the sample mean, our random variable, follows a normal distribution, then we can use normal distribution to find the probability that's associated with this x bar, as we have learned before. Let us begin with the first example here, which is talking about safe loading of elevators. The problem is a bit long. I'll give you 1 minute to read this description and talk about the two problems here. Okay, so that's about the capacity of elevator. If it comes with the label saying 4,000 pounds and 27 passengers, we can convert this to average 148 pounds per person, right? A mean passenger weight. So we can assume the worst case scenario here is the elevator can be filled with 27 adults. Okay, and the maximum weight is going to be 4,000 pounds the elevator can hold. So let's see how can we convert this to an normal distribution question. So assume that those like adult males have weights that are normally distributed with a mean of 189 pounds and a standard deviation of 39 pounds. Question A, we can find the probability that one randomly selected adult male has a weight greater than 148 pounds, as here we computed. Question B, looking at the worst case scenario, find the probability that a sample of 27 randomly selected adult males, okay, filled in that elevator has a mean weight greater than 148 pounds. So there is a slightly difference between A and B. The first case is you randomly take one individual from the population, okay, which is like adult male, this population. Question B talks about you are randomly taking a sample of 27 selected adult males from the population. So that's related to X bar. Okay. Over here, we're looking at X as the adult weights. Okay. So let's begin with the question 1. Okay. Find the probability that one randomly selected adult has a weight that is greater than 148. All right, so we're dealing with an individual value from the normal distributed population. Here we're talking about one individual weight, right? One individual weight. So we can sketch a normal curve as we mentioned before. This is the normal curve about individual weight of those adult males. Based on the description, they have a mean of 189 pounds and standard deviation 39 pounds. So you put 189 in the middle for that X. So here is our mean, okay. And here is x, which is the individual weight, okay, for one adult male. In this particular case, we're interested in 148, and we're checking what's the probability of one individual selected male has a weight that is higher than 148. So 148 is to the left of the mean, and you're looking at the chance of the weight being higher than 148. So to the right of this 148. So this is related to what we did before in last section. Okay, so let me scroll down this a little bit. We can convert this x to z, right? Because each x would correspond to a z. Over here, for x equals to, for mu equals 189, the z-score will be 0. For x equals 148, you would have a corresponding z-score, okay? And based on the conversion formula that we have studied before from last section, z would be x minus mu and divided by sigma. So we do 148 subtract 189 on the top, and then just divide by 39. We get negative 1.05. So here z is negative 1.05, being negative. So this probability, which is the chance of one individual male has weight higher than 148, can be computed from the StatCrunch. Okay, StatCrunch, which will be in this graph, as we just mentioned again. So let's use the StatCrunch here for the computation. Remember, z is negative 1.05. So I can convert this problem to the following mathematical expression, saying that probability of my individual weight higher than 148 is the same as probability of z greater than negative 1.05. Let me double check. Is that 1.05? Yes. Okay. And that can be computed by StatCrunch. So let's do this in StatCrunch. So equals to, so StatCrunch gave us the calculator here. Okay, so that's going to be standard and it's greater than. Check mean to be 0 and standard deviation to be 1. That is correct. And it's z is greater than negative 1.05. Compute the probability. The graph looks consistent to what we had before. So it's 0.8531. Okay. 0.8531, which means there's 85.31% of the chance 31% of chance that one individual male would have a weight that's higher than 148. Okay? So that's what we learned before, but this time the problem gets changed a little bit for question B. Okay, so question B. Question B, find the probability that a sample of 27 randomly selected adult males have a mean weight. Okay, sample of 27 randomly selected has a mean weight that is greater than 148. So the elevator now is full of 27 like adult males. We're looking at the probability that the mean weight is greater than 148. So we can try to think if we can use the normal distribution. All right, we understand the condition is we can use the normal distribution if the original population is normally distributed, or if the sample size is large enough. This example, we only have 27. Sample size is not large enough. However, the original population of males' weight is normally distributed, right? So the samples of any size will yield means that's normally distributed, which means our central limit theorem works here. Okay. So central limit theorem is checked, which means sample means are still normally distributed. Okay. And then we can use the conclusion from the central limit theorem. We would have mean of the sample mean and standard deviation of the sample mean being computed. Okay, let's continue this in the next video. So let's continue. As we just mentioned, the central limit theorem applies here. Therefore, the mean of the sample mean would be the same as population mean. In this question is 189. And standard deviation of the sample mean is going to be the sigma over root of n based on the formula that we talked about before, which is going to be 39 population standard deviation, and then divide by square root of the sample size. And we're assuming 27 people from a sample. So n will be 27. By doing that, you get 7.51. So which means this time if we look at a normal distribution, okay, we are looking at the distribution of x bars, okay, sample means. And the sample means has a mean of 189, as we mentioned here, 189. And standard deviation is 7.51, which is really small, right? So you would have a very tall normal curve. And in our question, we're interested in knowing what's the chance of having a sample mean of 27 people of their mean weight to be greater than 148. So x bar this time is 148, which is to the left. And we're looking at probability of, okay, let's see here. So probability of sample mean of 27 people having a weight greater than 148. Okay. So in order to do this, we're going to do the same thing. We're going to convert this x bar to z. Oopsie, that's not what my intention here. So I'm going to put the z here. So convert x bar to z. To z, let me see if I can activate the z again. So for an x bar to z, right? The formula this time, because we're working on sample mean, formula is going to be z equals to x bar minus mu of x bar divided by sigma x bar. So the formula is going to be this one. Let's see if we have that. Yeah, we don't have. So in this case, the mean of sample mean is going to be 189, as we see here. And sigma x bar, as we just did in the previous section, sigma x bar is going to be 7.51, which is 39 divided by root of 27. So that's what we are going to put over here, 7.51. So the z-score for that x bar is going to be negative 5.46. Okay? So I'm going to put here as negative 5. So here it has a z-score, which is negative 5.446. So the probability of x bar being greater than 148 is the same as probability of z-score being greater than negative 5.46. Okay? And again, this can be done in StatCrunch. So if we activate StatCrunch, we're looking at standard normal distribution for z. And in our case, we're doing z is greater than negative 5.46. So we do greater than negative 5.46. Okay? So it got you, the probability is almost 1 because it's 0.99999. If you round up, it's almost close to 1, right? I'm going to come back here. So 0.9999, almost 100%. Okay. Which is 100%. So in the next slide, we can say we are quite sure that if you randomly take 27 selected adult males, they're going to have a mean weight that's greater than 148 pounds. Okay, so the chance is 100% of the chance. So that means if you take 27 randomly selected adult, they are going to exceed that capacity. Okay. So interpretation for this problem, we can say there is a 0.8534 probability for an individual male to have a weight more than 148 pounds. And there is 0.9999998 probability that 27 selected males will have a mean weight of more than 148 pounds. Okay? And again, given to the safety capacity is 4,000 pounds, it's almost certain that it will be overweight if it's filled with 27 randomly selected adult males, as we just mentioned. All right, so that's one question, and we see that in this question, even though the question is about, in the question B, it's about the sample mean, but the way we do it is similar to what we had before. So we're still converting the x bar to z, and then we use the stat crunch to find the probability. Okay, in this question, it's almost 100% chance, right? So next question is about June temperature that we used before. All right, so the temperature in June is still normally distributed with a mean of 80% and standard deviation of 80 degree and standard deviation 4 degrees. And this time we are randomly selecting a sample of 20 June days, okay, from the last 50 years. We have a few questions here. First of all, does the sample mean follow a normal distribution here? Which means, can we apply central limit theorem? Right? Answer would be yes, because even though we have 20, that's less than 30 as sample size. But again, the original distribution being sampled, which means the June temperature, okay, the June temperature is normal. So central limit theorem still applies, right? Which indicates our sample mean would follow a normal distribution. Okay. Being a distribution would be interested in their mean and standard deviation of x bar. So again, mu of x bar would just be the population mean, 80. Sigma x bar is going to be sigma 4 and divide by root of n. So let me write the formula here in case you forget. So sigma x bar equals to sigma over root of n, and mu of x bar is just the population mu, 80. Okay. So doing computation, you can get 0.8944 for the standard deviation of the sample mean and mean of the sample means. So suppose we want to find the probability that the mean of our sample is between 78 and 82. So this time we're looking for probability of sample mean x bar that's between 78 and 82. And again, we're going to use this formula to convert the x bar to z. So z would be x bar minus mu of x bar and divided by sigma x bar, which we have computed in the previous slides. Okay. So we're going to convert 78 as one of the x, 78, to its z. Okay. Based on the formula, we do x bar minus mu of x bar divided by sigma x bar, we get negative 2.24. And then we're going to convert the 82 as x bar to its z. So just applying that formula again, you get 2.24. Okay? So this one we can just say probability of x bar between 78 and 82 is the same as probability of its z-score being between 2.24 and negative 2.24. Sorry, I'm running out of space. Okay. So go to StatCrunch and apply those two ideas in. Okay. So it's about z and it's between, right? Negative 2.24 to positive 2.24. In between for its probability. Okay, in between, the chance is 0.9749. So 0.9749 is going to be the probability. And we see that these two z's goes in here and here. Okay. All right, so that chance is 97% of the chance. And once again, we can still use the quick check, right? We can still do the quick check. Let me here. Let's do this. For the quick check in StatCrunch, you can do that real quick by changing the mean of sample mean and the standard deviation of sample mean. So let me illustrate how we do that. So mean of the sample mean this time is going to be 80. standard deviation according to the computation is going to be 0.8944. Okay, so change those two values, and this time you are interested in the sample mean itself. So it's going to be between, according to the original question, we're going to do between 78 degrees and 82 degrees. Okay, so we do 78 and, oh, in between that. Yeah, 78 and 82, right? 82 and hit compute. You get the same value, 0.9746. Okay. So it's the quick check, but for your graded homework, you do need to submit the work as we did here. So convert X bar to Z, and then find the probability in StatCrunch. All right, we have another example here. Okay, talking about suppose the mean number of people who withdraw from average number of people who withdraw from an introductory stats course at large schools, okay, is 18 with the standard deviation of 4.2. And this time, if we take a sample of 36 classes, we would like to find the probability that the sample mean of the 36 classes, so sample mean number of people who withdraw from the introductory stats course, would be more than 20. In other words, find the probability of the sample mean X bar is higher than 20. First question we should think of is, can we use central limit theorem, which means can we determine that X bar would follow a normal distribution? Question mark. Okay. And this time we have a sample size of 36. Okay, sample size of 36. Oopsie. Okay. So 36 is actually great enough, right? 36 is already greater than 30, so that's a large sample size. If it's large sample size, then we say the distribution, yes, is approximately normally distributed. Okay, which means we can compute the mean of the sample mean and standard deviation of the sample mean based on the previous example. So mu of X bar would be the same as mu here, which is 18. Sigma of X bar would be sigma 4.2 divided by root of n. You will be getting 0.7. Okay? Alright, so next slide is just talking about the way we do it again. So, excuse me. So probability of X bar greater than 20 is the same as probability of converting the Z to the Z-score, which is going to be 2.8571. If we use the StatCrunch, you can see this is going to be your Z-score. Okay. About standard normal distributions. It's going to be greater than 2.8571. This probability based on computation is 0.0021. Okay, and again, the way we do it is going to be using the StatCrunch and convert this to standard normal distribution, so 0 to 1, and Z is greater than 2.8571, and hit compute. That gets you 0.0021 as what we have illustrated in this PowerPoint, 0.0021. That's almost only 0.21%, right? It's even less than 1%. So suppose we did a sample of 36 introductory stats course, and we found the sample mean was indeed 20. Okay, was indeed 20. Would that be unusual? Yes, it will be unusual because as we computed, the probability is going to be very small, right? This probability is 0.0021, which is 0.21%. This is less than 5% as the cutoff probability for rare events. Okay? And therefore we say this is unusual, right? This is unusual. We have one final example here. Okay. I'll give you 20 seconds to read the problem, and we'll come back real quick. So one last example that we have here to help you to understand whether you should use central limit theorems or not. Okay. Still suppose that the mean number of people who withdraw from the introductory stats course at large schools is 18. Okay, so mean number is 18 and standard deviation is 4.2. What is the probability that one individual class, because one class will have more than 20 students withdraw? Now, for this problem, we're assuming a normal distribution for the number of people who withdraw from intro stats class. So in this example, you may see some similarities of this example with our example 1 when we talk about the weight of the elevator, right, for one individual. So we are not actually finding the probability of a sample mean. Okay, so not looking for a sample mean. So the central limit theorem doesn't apply. Central limit theorem only applies to anything that's related to sample mean. Okay. So in this example, they're asking for one individual observation that is going to be X. Okay. And this is related to what you had learned before from the application of normal distribution, the last topic. So we'll just be using the method from last time again. So we convert the x back to z by using the formula that we did before, z equals to x minus mu divided by sigma. Therefore, the general mathematical expression we're going to carry this out is going to be probability of x greater than 20 for individual one class, right? One class equals to probability of z and greater than x minus mu 18 and divide by 4.2 equals to probability of z that is greater than 0.4762 by using the calculator of computing this idea of 20 minus 18 divided by 4.2. So let's apply to the apply this to the StatCrunch. So again, we have this is going to be standard, right? Not between, and x is greater than 0.4762. So 0.4762, hit compute. That's going to give you this probability here, which is going to be 0.3170. Right, which is going to be this number. Okay, that's 0.3170. And again, if you recall the quick method that we learned last time for last topic, you can always verify this in the StatCrunch by changing the mean and standard deviation. So if we revisit that method, we're going to have mean that is 18, standard deviation is 4.2, and we're interested in the number of students who withdraw from the stats class being greater than 20, right? Compute, it's going to be 0.3170 again, the same answer, okay? So this time you see the chance is much bigger. It's almost 32% of the chance, right? 32% of chance compared to what we had before of a sample of 27 27 classes, 36, my bad, 36 classes to have more than 20 students withdraw on average, right? So that's the end of the section, and this section combines the information we learned last time as well as new material. And actually the only thing that's new is we want to mention if you're doing with anything about the probability of sample means, then you should consider whether central limit theorem can apply. If it does apply, then we compute the mean of the sample mean based on population mean, and standard deviation of the sample mean is sigma over root of n. And then the rest of the procedure is the same as what we did before. All right, that's the end of the section. Thank you.